Okay, so today you can see that I made progress um, from last time trying to tear this into the basics of the basics of the basics. And uh, this will be a little bit rough because I ran out of time. And next week, everything will be pinned down. Of course, I might pin it down so much that I find some problem with it, but right now it looks good to me. So we're talking about a rather dramatic improvement. So let's talk about this. Um, uh, so now the title of chapter 5 has changed uh, because I found a way to tear this apart so there's no point in talking about free choice functions. It's more basics. So I had to come up with a title for chapter 5, and I think the right title is probably explicitly pi 01. Uh, I'll explain a little bit later. I don't know what's going to happen here, but if this is right, and I made this a big an advance, uh, I'd like to think that there would be one in here. But that remains to be seen. We're still talking about this. Now, in this new version, quite a bit is the same. There's this introductory machinery I need in set theory. So this is pure set theory here. Oh, well, it's pure set theory, but then I pull the elementary embeddings down to the upper shift. So the upper shift is acting like a an elementary embedding. Now, um, I had to fix this a little bit. I haven't made, I did it much clearer. I had it sort of muddled before. So we're going to go over this a little bit, but we won't spend a lot of time on this. But I do want to give this, I revised the statement here so it's clearer. This. All right. So the name of this approach is called two free choice. And you'll see why when I actually go do the details. Uh, so there are two elementary statements which are very beautiful undergraduate exercises. Undergraduate exercises with hints. I don't think the undergraduates may not be able to do this readily, but you have to give them a hint, and then it's very gorgeous. Uh, this is general on any relation on any set. And there's a dual form of it. There's a dual form of it. Then I extend it with structure, and this is the magical pi 01 sentence. This is the magical new incompleteness. It's called OI. That means order invariant. That we've used that forever. OI 2 FRCH. That means two free choice. You'll see why I call it two free choice. And then the upper shift is a vital element in the statement. Whereas over here, there's no structure. So there's no notion of order invariance, and there's certainly nothing like the upper shift. Now, this leads to the question of what other settings and what natural maps in mathematics can you use here? I want to get one thing done at a time, this book particularly, before one ventures into this, but this does appear to be exciting. Okay, so then there's the dual form, and as you'd expect, these are trivially equivalent, these two. Um, then I actually prove this statement from elementary embedding upper shift. Well, that actually proves it from con SRP, right? For this chain. So we know the statement is follows from the large cardinals. Then we want to do the reversal. Uh, and that means, in fact, equivalence, right? We want to do the equivalence. And that's what this chapter is all about. This is the key chapter. So we develop a thing called resolution sequences. And the point of resolution sequences is to approximate this infinite statement. This infinite statement is a trivial variant of something that's in chapter 3 and reversed, and therefore reversed in chapter 4. So we already know that this is strong, and it's an infinitary statement. We approximate it by what's called resolution sequences. We approximate this infinite statement by what's called resolution sequences, which are sequences of tuples, k-tuples, which are sequences of tuples, which are concatenated into one long tuple. All right. So there's resolution sequences and resolution tuples. When I exposit this cleanly, I mean, I'm not at the point of slick enough exposition yet. I'm just trying to get this thing checked and I get a solid draft with all the details. But then there's some massaging of it to make the notions clearer would be in order. Resolution sequences as opposed to resolution tuples, for example, something like that. All right. So once we have these, this is the really key construction. I've got to show that my statement that I'm trying to reverse implies that all these approximations hold, that all these approximations exist. I have to do that. This is the heart of the matter right here. Okay. And then after I do that, I have to show how I use these approximations. So I actually use these approximations to get a weak form of the statement of one of the statements in chapter 3 that's reversed in chapter 4. A weak form, I call it, I just put the word restricted on there. And this is something that came up once in an earlier draft at the end of chapter 4, where I had to actually literally go in to the reversal and start saying I only need to do this and all this. It was just a very unpleasant thing. So I managed to avoid that, by the way. I found a beautiful to me way of avoiding that problem by doing it abstractly, using some interesting, perhaps not completely known model theory. All right. Anyways, so I show that these resolution sequences, these approximate things, these give me the infinite statement. Not quite the one I want. I want the one without the restriction. And then I show that the restricted one implies another one that's less restrictive, namely that something is dense, actually. I used to say, I don't know if you remember these lectures, I used to say the problem with this thing is I don't have density, but I can still do the reversal, and I had to do a lot of hand waving and looking at massaging a giant proof, and I didn't really like that. So I've got around that. I can get density, and then density does trivially give me, this is actually very easy, does give me the full thing. So then I'm done, because I have a big chain of implications, this and this to this, 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 and this to this. And then it's rather easy to show that this implies a statement literally in chapter 3, and then the final implication is chapter 4. It comes from chapter 4 that you get con SRP. So you have a chain. I don't know what the length is, 10 or something. You get a chain so they're all equivalent, because con SRP is, we started with con SRP and we end with con SRP. And then I make some comments about how this is explicitly pi 0, 1. Well, it isn't really. It's actually pi 0, 2, but you can trivially put bounds on it, or you can quote quantifier elimination for rationals with order, or you can alternatively do it a little differently, where the relation is on a nice finite is on a particular finite set. So there are all these variants, some of which are explicitly pi 0, 1 in the strongest sense. But you know, this is just cleaning, house cleaning. And then this equivalence, by the way, is doable in PRA, and that's because WKL naught is conservative over PRA for uh, pi 0, 2 sentences, and this equivalence is pi 0, 2. Now, I don't know what's going to happen here. It's a little hard to compete with this drama, but I could. It could be, for example, that this rotation method, which we haven't talked about yet, this rotation method actually, which is a very pretty algorithmic, non-deterministic algorithmic idea, this rotation method might actually get to be independent when I just do it once or twice. In other words, it's a sequential process, and I actually can do it any finite number, any infinite number, even infinite number of times. But maybe I could just do it once and it's independent. So this will be another bombshell uh, thing, uh, maybe even competing with this in some way, or being at least a rival of this. So stay tuned. I haven't really reconsidered this stuff down here. All right, so let's see what we can say here. Now, I apologize. This is not, I had no chance to format this and so forth, but I got you can get a pretty good idea of how this works. Of course, this now the stakes seem to be rather high, and I really got to roll up my sleeves and check everything. Now, one of the things that's kind of eye-popping to me is that I think I can use all of Q for this, um, which is nicer than having minus KK, which is what I normally do. I have an interval with endpoints, and that's very important in many ways. But on the other hand, it appears that the machinery of all that somehow is embedded in this statement, which is kind of surprising to me. So I'm going to have my eye out looking very carefully that I'm going to be able to do this without writing something like minus KK here. And that it makes it more beautiful. The more beautiful, the better. All right. Okay. So I didn't even mean to talk about this. This is just, I haven't even written the introduction. I just recorded this statement so you just know what's going to happen soon. I just recorded it. We'll talk about more more about this from fresh later. All right, so I really want to talk about elementary embeddings first. And the elementary embedding statement is that there's a countable model of ZFC with a satisfaction relation and non-standard integers. I don't think it's important that they're non-standard integers, but they're going to have to be them because of the satisfaction relation being provable in WKL naught plus con SRP would have to be non-standard integers. Otherwise, WKL naught wouldn't be enough. So I don't want to go into detail because I already did this particular thing. Yeah, it may look familiar to you that you can do this. I don't really want to say much about this. It was somewhat a little bit non-straightforward to do this. Uh, but I do want to say something at the end. I don't know whether I think I do need, there's some role of V equals L in all this. It might be eliminable. but that's not a worry. I develop indiscernibles, and from the right kind of indiscernibles, you can get a elementary embedding. Um, okay, so that's the statement. Not quite. There's the elementary embedding. Yeah. So we get down to here. There's a countable model with satisfaction relation elementary embedding with the iterates are at the critical point or unbounded. You can even have that. Actually, yeah. Yeah. I think you want that. All right. But now we have to push it into the rationals. Remember, it's a countable model, this elementary embedding thing. It's a countable model. We have to push it into the rationals. And what becomes of the elementary embedding? The idea is it becomes the upper shift. But before I was worried about trying to make the elementary embedding total. It's important not to have it total. I didn't quite set this up right. I fixed it now. Uh, we define the upper shift. This is vital. Now I do some combinatorics so I can pull this into the upper shift with a technical lemma, looking at threads or what. Threads is probably not the right word. That has some other meanings. Looking at the orbits under J. See, some of these orbits don't go back all the way. They only start at someplace because J is not onto. The elementary embedding can't be onto. All right, so we get an isomorphism from this structure um, onto this. E comma less than comma 0. In other words, C, the critical point C goes to 0, and the function J becomes the upper shift restricted to E. Upper shift restricted to E. And now we finally get the statement that I really want. There's a countable model M of ZFC where the domain of M intersect the rationals is exactly the ordinals of the structure. And the ordinals of the structure are between omega, contain omega with satisfaction relation where the upper shift restricted to the ordinals. I don't care about how the upper shift works elsewhere, is an elementary embedding of M for tuples, elementary embedding just for tuples of ordinals, just for tuples of ordinals. That's all I need. So this model M, picture of it as follows. Look, its domain consists of some rationals, some messy set of rationals. Some messy set of rationals together with some non-rationals, some side points. So the ordinals are going to be rationals only. Okay. And then the upper shift acting on those rationals, that's the only place that upper shift acts on the rationals, is exactly uh, is an elementary embedding. In other words, it preserves M formulas. It preserves M statements, but just on the ordinals. In other words, I don't care about the non-ordinals. Okay, that's a better way of saying everything than I had before. Okay, and then we can use that. That turns out to be very useful. We never use the sets in this model that are not ordinals. Okay, all the action is on the ordinals of the model, which are rational numbers. All right. Now, let's talk about two free choice. So as a preview, we proved the two free choice theorem. Very beautiful. I mean, whether it was explicitly stated, um, it could well be, but it's absolutely gorgeous undergraduate exercise, at least with hint. And it's dual in ZFC. These theorems are on an arbitrary set X with no structure. Okay, and then we put some structure on, and we get the statements that are independent of the axioms. All right, so let's talk about this dual. Okay, in every reflexive symmetric relation on any set, any 2 points are respectively related to some other 2 points, some 2 points are respectively related to some 2 points, X and Y are respectively related to some Z and W, where Z and W form a free set. Very pretty. And the dual is in every reflexive symmetric relation on X, any two X and Y are respectively free with some Z and W, where Z and W are related. And this is the dual. And what I do is I sketch in the thing, I sketch, which I can sketch for you right now. I sketch the undergraduate proof of both of these things separately. I don't try to prove that. You can also prove that these are equivalent in advance by general nonsense. I chose to prove this one and then separately prove this one by just changing some words instead of abstractly proving their equivalent. All right. So what do you do? How do you prove this statement? You take a maximal free set. Maximal free set. Okay, Zorn's lemma, whatever you want. You take a maximal free set, call it S. And now the basic property of a maximal free set is that every X is related to some element of the maximal free set. Remember, we have reflexive in here. Okay. In other words, every point is related to an element of this free set, right? This maximal free set. So given X, just pick something in the maximal free set, pick Z to be in the maximal free set related to X, and pick W to be related to Y, where W is in the maximal free set. And since they're both in the maximal free set, they must be free together, because the second system of ZW is a subset of the maximal free set. All right. Okay, so there you are. It's nice to be an undergraduate. All right, now the dual is in every reflexive symmetric. And by the way, if you actually really write this out, think about it, think it through, not only do you use reflexive, but you are also going to use symmetric. You have to use symmetric. All right. All right. Now, the other one we can prove as follows. I take a maximal, what I call root. A maximal root, meaning a root of a relation is a set such that any two things are related. So I take a maximal root. And then the key point about a maximal root is that every point is free with some element of the maximal root. Every element is free with some element of the maximal root. And for X to be free with Z just means that either X is equal to Z or X and Z are unrelated. All right. This is in total consonance with the way free is used in mathematics a lot. All right. And so therefore, once again, you just take X and you pick any Z that's free with it, that's in the maximal root, and given Y, you take any W with it that's free in the maximal root. And then you get Z and W are in the maximal root, and therefore they're related. Okay. By the way, in the section where I talk about variance, I'll do this for graphs. There's a statement for graphs like this. In any graph, uh, any two vertices are respectively uh, detached or respectively uh, all right. I may have to need a notion of uh, yeah, what's the best way to do this? See, in graphs, you have adjacency, which is strict, and then you have non-adjacency, which is not strict. That's right. So every X and Y are non-adjacent, respectively, to two things, to Z and Y, uh, uh, where Z and Y are uh, adjacent, right? Okay. Look, let me not make a fool of myself with this. But anyways, I will give the form for graphs, which is a similar flavor. Might as well, because a graph is just an irreflexive symmetric relation. All right. And by the way, I handled graphs in the chapter 3 and 4 where we have reversals. Okay. All right. Now we get to the variant. Here it is. And if I keep the screen up, yeah, good. You can see on the one screen. You can compare this with this. So in every reflexive symmetric relation on X, any two X and Y are respectively related to some Z and W, where Z and W are free. In every reflexive symmetric or ordered invariant relation, now on Q to the K, any two X and Y are respectively related to some Z and W, where Z and W are not only free, but that you would get from before, but Z and W and the upper shift of Z and the upper shift of W are free. By the way, I suspect because I mean, or I tried to prove this, this will be independent even with one of these terms missing. That I suspect that may not be, it may be provable. That's that would be kind of a beautiful addition. Not that I'm going to, I think I won't really work on this. But you know, showing that if you drop one of these two terms here, one of these juicy two terms, uh, that uh, that it's provable, could well be the case. Um, if I just had Z and D, both these, uh, then I would get Z and W are free. I think maybe some of these subsets might actually be independent also. I mean, I think that I'll look at, and some of them are not. But anyways, this is the prettiest one. ZW, upper shift Z and upper shift W. And then there's the dual. The dual actually is easier to reverse. It turns out for technical reasons, it's a little clearer. I mean, you can reverse both of them by just changing the words, but conceptually speaking, I prefer to reverse with a dual. In every one, any two X and Y are respectively free with some Z and W, where Z and W, upper shift Z, upper shift W are mutually related. Okay, I may not be able to improve on this. Uh, that's a little. All right. Anyways, um, now there's a soft trivial proof that these two are equivalent. So I prefer to do that rather than repeat any long reversal or proofs. So we do have this, which is very easy. All right, so now we have to actually show this statement is okay. And actually, this was harder than I thought. I originally overlooked a subtlety, which I had to deal with, and apparently successfully. But all that has to be written out. Not, and I haven't done that completely, but I got the lemmas and everything. All right. So what happens is there's a weak form of this. So okay. So let's assume elementary embedding upper shift, and let's let M be given. Let's take the data from this statement. So we have a countable model M. The domain intersect the rationals is the ordinals. Yeah. And then the ordinals are contain omega through Q. Uh, uh, the zero here is already a big ordinal. It's called the critical point over here. Yeah. I mean, with satisfaction relation, where the upper shift restricted to the ordinals is an elementary embedding of M on the ordinals. Let E be the ordinals. And uh, we first prove Why did I say that? Because I was thinking about the dual. Dual automatically comes here. We now prove. Okay, now we're going to prove it, but we're going to prove a modification of it first. And then we have to show it's the real thing. So the modification is that we are living in E. In every reflexive symmetric order invariant relation on Q to the K, every X and Y in E to the K. Remember, E is borrowed from this statement here. Every X and Y in E to the K are respectively related to some Z and W in E to the K, where this whole thing is free. Okay. We won't work with a dual. We only work with the dual of this stuff here. The dual of this. We only work with the dual when I'm doing the reversal, but we're not doing the reversal, we're doing the proof right now, the derivation. All right, so what's the problem here? I'm insisting that the X and Y I'm starting with are in E to the K, whereas the real statement has X and Y arbitrary elements of Q to the K. And this is not such a nice thing because E is easily seen not to be dense, for example. I mean, E is just some sort of incredible set theoretically motivated mess of rationals. So there's something to do. So the proof of this is very easy. The proof of this is like the undergraduate exercise modified. So let's talk about what I mean by that. Instead of taking a maximal free set under the relation, and remember we're in M, the model of set theory of ZFC. Instead of taking a maximal free set uh, of tuples of ordinals uh, under the relation, we take, no, I'm sorry. We actually take, we do that. We take a maximal free set, but it has to be M definable. So we can obviously make an M definable maximal free set, right? Because we're in M, we're in set theory. We just build it transfinitely, and that's M definable without any parameters. Okay, fine. We definitely have that for every X in E to the K, not for every X in rationals, only for internal X. So for every X in E to the K, because E is the internal ordinals, right? Here. So for every X in E to the K, it's got to be related to something in the maximal free set, right? That's always true when you have a maximal free set. Okay, so X is related to something in the maximal free set. Y is related to something in the maximal free set. That means X is related to Z in the maximal free set. Y is related to W in the maximal free set. Therefore, Z and W are obviously free, right? This is just the general undergraduate stuff, right? But I can also make them free with the upper shifts. Why can I do that? Because the maximal free set is closed under upper shift. Why is the maximal free set closed under upper shift? Because it's definable without parameters. So anything that holds of Z, in particular being in this thing, must hold of the upper shift of Z. That's what the elementary embedding condition is on upper shift. So that's why I can get Z and W and upper shift Z and upper shift W free. So this is just an elaboration of the undergraduate thing, as long as but you have to understand what an upper shift is and well, you have to understand what elementary embedding means. Yeah. Okay, so that's clearly fine. But now I have to figure out how to get rid of, so now I want to uh replace E by Q in both places, right? This is what I have to do. Replace E by Q in both places, and then I'm done. Okay, so this turns out to be a combinatorial thing with model theoretic overtones of some sort. So the important thing is I have to define a similarity relation between rational vectors. So they're the same length. Each floor of xi is the same as the floor of yi. The negatives are exactly the same, which is something inspired by the upper shift, right? Because the upper shift is the identity on the negatives. See, I didn't format this for you. I hope you don't mind. I just ran out of time. This is what I mean by formatting. Okay. All right. And the fractional parts are order equivalent. The fractional parts are order equivalent. This is the notion of similarity. Now, it's the same thing as saying that it's floor preserving. This is really the same as saying that it's floor preserving and that within each interval, it's order equivalent. So in the full exposition of this, I will, say that that's equivalent to similarity. Remember, I have to transfer between M and the rationals. So I need some lemmas, and since I'm running out of time and I do want to get to some other principal points, I'm just going to briefly go through, say what it is. If I have two similar X and Y, then they satisfy the same formulas with the upper shift. And that's what I'm interested in. I'm interested in the formulas that you can describe in the upper shift with less than in the upper shift. So I can apply this machinery. If X and Y are similar, and if I have a Z that I want to extend, given any Z, I can always find a W such that X and Z and Y and W are similar. Yeah. This extension property is important. Also, every tuple is similar to a tuple in E to the R. Every tuple is similar to a tuple in E to the R. That uses very simple properties about E, almost nothing. Just that there's infinitely many things between any two non-negative integers. This is all you need for that, really. Well, No, I think maybe you may need more that this is closed on the upper shift. Yeah. Yeah. But anyways, all of this will be written out in gory detail. All right. Now we get that we can get the full statement. Yeah, there's a way. I wanted to talk about it, but I don't have time. There's a way now to use this machinery to prove this statement without the e's, where e is q. The idea is you start with an arbitrary x and y, and then you take the tuple x y. You take x comma y concatenated, and find a you find a similar thing with E because of this lemma here, this 334. Whoops. 3, 3. What did I do? This is 3. This is 4. This is 5. Because of 5, because of 4, we can make them into E. Then we can apply the theorem for E and you get Z and W in E. I actually don't even need that they're in E. And that Z and W then can be uh, shown to work in the rationals because the order equivalence is the same. All right, let me not go into that any further. But anyways, you can do that, and it'll be fully checked next time. So now we've actually finished the proof of this thing. Now, what was the promised title of? I think I see something here. 5.4. Okay, that was the title, and this is makes no sense. This is a prior notation. All right, let's keep this title. All right. So now, in this section 5.4, which has many subsections, we do the reversal and, well, the equivalency even. So we reverse by deriving one of the statements treated in chapters 3 and 4, and there are several steps involved. It's most convenient to target this statement. Every ordered invariant relation on minus 1, 1 Q, K has a maximal root. This is a statement that's almost the same as the statement in the yeah, no, sorry. This is actually literally in chapter 3, treated in chapter 3 with chapter 4 reversal. So we're home free if I can reverse this, go from here to here. Okay. Now we can multiply through by K, and this is trivially equivalent to this, where that the notation of that is clear. Right? So we actually work with this. It's easier to work with this. Okay, so we develop a thing called R resolution sequences, and then R resolution tuples in a better exposition will also be mentioned. R resolution sequences that serve as finite approximations to the target statement. And uh, let's see if I remember right. I didn't do there's screwed up. I did it a little differently. It's not anything really serious. Okay, so we're going to develop a statement that resolution sequences exist that have nice properties. Uh, and we prove that from the dual of this. And RS is revolution sequences. The passage from having these resolution sequences to the target statement is not straightforward. We need a weak form of this, a weak form of this uh, and this statement is has the word restricted in it, and it's easily derived. This is an easy. This is the easy one. This is direct compactness or Koenig tree lemma or whatever. Uh, Straightforward that you get into this. And restricting here means that instead of working with a space minus kk, we're only working with some e to the k, where minus k, 0 through k are in e, and e is contained in minus kk. To bridge the gap here, it's not easy to swallow this whole. We have an intermediate statement with density, and we get that from the restricted one. Uh, and then and then uh, we get the full thing from the dense one. Okay. All right. So let's talk about resolution sequences. Um, I use x square brackets I for the ith term of lists or sequences instead of xi. So there's a kind of dovetail thing I need to do. Uh, See, what's going to happen is I'm going to build sequences of k tuples, or sequences of n tuples, actually, sequences of n tuples. And at every stage, I'm going to handle, whatever that means. I'm going to process, at every stage, I'm going to process some tuple that's built out of the earlier tuples. And I want to do this in such a way that things dovetail. In other words, as I go out here, I'm getting more and more of the stuff from here. And so in the limit, I've handled everything in in the limit, I've handled everything in the every k tuple, every n tuple in the field of what I built at the end. And that's exactly what this restricted uh, statements are like. That I use the word restricted. Okay, so I need to know that I can keep building that, right? In other words, it takes care of all the earlier stuff slowly. There's a exponential factor. This thing goes out and you get more and more. All right, so uh, yeah, and the way to set this up is given any sequence anywhere, how do I describe what the candidate is that I want to process on, which has to be built from it's going to be built from all the terms of the previous tuples. So yeah, I have to look at positions inside the tuple, inside the master tuple when I smash it and take its concatenation. I have to talk about uh, the terms and in terms of their index. So this requires an ordering less than star. This is an ordering of the k tuples, uh, positive ones, because remember these are supposed to denote positions in tuples, positions. So if I have a sequence, uh, okay, so alpha, we define alpha of x1 through xm. That means the candidate from x1 through xm. Uh, the candidate is obtained from all of them by writing um equals I1 through IK and forming this. In other words, this tells me uh, which this tells me which uh, which elements am I going to pick from, and I just need that to be inclusive, that all possible sequences of positions are represented in a decent order. All right. So then we can define the resolution sequences. So these resolution sequences are made of n tuples, and they start off with n plus 2 to the m. They start off with n plus 2 to the nth power uh, tuples, which simply list all of the n tuples from this set in order by less than star. So just do that, and uh, then the real action starts later. This just starts with some basic material, so to speak, and then in other words, just these, and then we process by either throwing somebody in, by throwing the candidate in, or taking something not related to it and throwing that in, right? Throwing that in. So xi plus one is either it's either the candidate or something related to the candidate. Okay, and of course we want that all of this really good stuff forms a root. Now that's just the definition of a maximal root, but it's only approximate. So in the limit, if you go to infinity, you're going to get a full-blown maximal root. Now it won't be maximal in the entire space we're interested in, which is a dense space, minus n to n in the rationals, but it'll be only dense in some sort of set that contains 0 through n. It'll only be dense in the nth power of some set, right? It would be maximal only in that. Now, of course, I don't know that there's any kind of I don't know. Actually, what's critical here is that we're only, although it was not important to do it this way. I decided to do it this way. We're only looking at this. We're only looking at where the non-negative numbers have to be among 0 through n. Okay, so in other words, these sequences only bear down in this situation. This turns out to be good enough in the limit. In the limit, you're going to get something that's maximal in all of this together with this, but there's an intermediate step you can always extend. It's like every filter can be extended to an ultrafilter, that kind of thing. You can always extend stuff uh, you can always extend at the other non-negative numbers, because the other non-negative numbers don't affect the invariance. I mean, well, we haven't talked about invariance yet. The other non-negative numbers, you'll still get a root. You'll be able to extend it to a maximal root that involves all of the numbers between 0 and n. You won't be able to fool with this though. That's different. That might you could fool with this. You could fool with all this, but now the issue is you want to make sure that uh, you can do anything you want here. The big problem is what you want is this to be invariant under the upper shift invariance. That's the problem. You're not going to get that from this. This is just a setup that requires only RCA naught. I mean, EFA, practically nothing, right? Okay. But now the word regular is comes in. Regular is what we really want. Regular means that the up that all of the good stuff in here, the serious stuff in here, together with their upper shift, forms a root. That's the kicker. That's the hard thing to get. Now you can't, turns out you can't be getting this without large cardinals. So, uh, but I claim that we can get it from our statement that we're trying to reverse. All right, so we have this statement that every reflexive symmetric order invariant relation on minus n to the n has a regular RNM resolution sequence that has to be regular. Uh, so that's what we actually want to prove from the statement we're reversing. Now, this is going to be tricky. I think I'm running out of time. Yeah, I was going to get to this crucial place. I can't say too much about this, but it would take at least 15 minutes to say. But this is really where the tire hits the road. I have to come up with a fancy relation, which does the magic. Uh, and I've checked this a lot in my head. Um, I've almost written it down, and this is really where the where I had to adjust things so that this would work. Uh, so I think rather than go on about this now, I think let's postpone this till 1 week today. Uh, yeah, and then there's some cleanup here because I still have to get I only get this restricted thing, and then I have to get the unrestricted version, and then I'm done. Okay, thank you. I'm Andreas, I'm done.